I thank you, Matt, for the introduction, and thank you to Chonghan as well for the invitation. I know this talk is a bit overdue. I think back in spring is when we originally had scheduled it, so I'm glad to be here today. I'll be talking about joint work with Shane Henderson, who was my advisor at Cornell, and the title here is Posterior-Based Stopping Rules for Bayesian Ranking and Selection Procedures. I think it's probably a good idea if there are questions along the way to ask them, and I'll hopefully explain anything that's unclear. So I wanted to begin with an overview of where this talk is going so that you know what to look for along the way. We'll be studying a certain class of algorithms known as ranking and selection procedures. And these procedures deliver Bayesian statistical guarantees by tracking a posterior quantity and ultimately checking a stopping rule that determines whether to stop or not. And what we found to be the common practice out there in the literature is to, instead of computing these posterior quantities, one derives a conservative bound, usually using Bonferroni's or Slepian's inequality, and then uses that bound as a surrogate. So you go along until this bound crosses some threshold, and then you terminate. From what we can tell, the tacit assumption underlying this approach is that the posterior quantity is being perceived as costly to compute. But in this paper, we'll come up with some ways to show how posterior quantities like these can be computed at modest cost using numerical integration. As a result, by using the exact quantity, we'll show that in some instances, this leads to substantial savings in the runtime of a procedure. And we can actually even get further gains in computational efficiency by making sort of clever use of a Monte Carlo estimator. So the space and work in which I do my research is optimization via simulation problems. And these arise when you're trying to make a decision under uncertainty, typically involving a complex system. A complex system being one that you may not have an analytical form to express some output or performance measure. And so you might resort to running a stochastic simulation, taking replications to get an estimate of the objective function value at different feasible solutions. For the purposes of this talk, I'll be considering the case where you have a single objective function that you're trying to optimize over. To give a concrete example of an application where this arises, think of positioning ambulance bases in a metropolitan area, where here the choice of where to put ambulance bases dictates what your response times are going to be across a city. And here this system is subject to stochasticity in terms of when calls arrive and where they are called from. A natural objective here might be to position ambulances in order to minimize the expected call response time. So here the expected call response time is our performance measure. And in order to estimate it, we would run a simulation model, multiple replications of say a day or a week of ambulance operations in order to see what the call response time is associated with a particular arrangement of ambulance bases. For these kinds of problems, one approach is ranking and selection, which takes the view of restricting attention to a finite set of alternatives, or you can think of them as feasible solutions. And then I'm going to use stochastic simulation to evaluate their performance and ultimately select the one that looks the best. There are sort of two competing views for how to tackle these problems. One is a frequentist approach, the other is the Bayesian. I'll be focusing exclusively on the Bayesian treatment of ranking and selection in this talk. So the Bayesian view is to regard the performances of alternatives, which are unknown to us, as random variables. So if we have k alternatives, k solutions, I'll let wi denote the performance of alternative I, and let bold W be the vector of all of the performances of the k solutions. So bold W here is the unknown problem instance. Then I'll also use some notation here when we care about ordering the performances of alternatives. We'll let subscript brackets denote those orderings. So here, W brackets K is the one with the highest performance. And I'm going to assume without loss of generality that larger performance is better here. That's how the equations in these slides are going to be set up. So for among the K alternatives, alternative bracket K is the best, or if there are ties, it's one of the best.
So David, did you say that WI is the expected value of the performance measure?
Mu I is, yes, the expected performance, so expected costs, expected profit.
Yeah, expected.
Yes.
The way it is stated, it sounds like a random variable. So anyway.
So from the Bayesian point of view, we treat we're treating the unknown quantity, what would typically be mu in the frequentist case, as a random variable. And so we're going to learn about it and update our uncertainty regarding the unknown expected values.
Okay.
Yeah. And so it looks very different in terms of notation and sort of conceptually from the frequentist setup for the problem. So the Bayesian approach is sort of standard here. The decision maker starts with a prior distribution on the unknown problem instance, generate data, obtaining observations, which we'll think of here as being simulation replications from the alternatives. And then you sort of turn the crank using Bayes' rule, the standard Bayesian machinery, to update your posterior distribution of W. And here we're looking at running a procedure like this until we satisfy some stopping rule that can be checked by examining the posterior distribution given the data that we've observed. So if the stopping rule isn't met, we continue, we take more data and update it until we can stop. So I'll introduce just a bit more notation here and put the assumptions up front that lead to the results in these slides. So for a given alternative I, one is generating simulation replications whose outputs are denoted by xij. So for the jth replication or jth observation, xij is that for alternative I. I'll let xi with an arrow over it just be the sequence of outputs from simulating alternative I. So the following three assumptions are fairly standard in the ranking selection literature. They lead to a lot of nice analytical results. So the first is that we're simulating IID replications from each of the alternatives, and that they're also normally distributed outputs. Here, the normally distributed outputs assumption is often predicated on sort of an argument that I could always batch outputs from replications to form sort of batched estimators, which by then appealing to the central limit theorem should be approximately normally distributed. This one is often used to get nice analytical results. The second assumption is going to be that different alternatives are simulated independently. So I'm precluding the use of common random numbers across alternatives. And the third is going to be that the decision maker has independent prior beliefs about the performances of the alternatives. So these last two, assumptions 2 and 3 together, will give us the nice property that the posterior distribution of our unknown problem instance has a product form. So it decomposes into essentially a product of marginal posterior distributions for each alternative.
So what about the case where there are some commonalities between the alternatives? So for example, my ambulance basis, between alternative 1, alternative 2, I have some common basis, for example. Does that introduce any kind of dependence between the alternatives?
So here the modeling assumption that we're making here is that we're treating performances of alternatives as being independent, though if you had that kind of relationship in the Bayesian framework, you might be able to incorporate that knowledge into your prior distribution. I'll relax some of these assumptions later in the talk or show how you might proceed if you do have either, say, I guess, alternative or assumption 3 in this case, not being satisfied.
Okay.
So to get a concrete idea of what these posterior distributions look like under this setup, if you were to walk in with a conjugate reference prior, sort of a non-informative prior, and take NI observations from each of the alternatives, then the sample mean and sample variance that you get from each alternative are what's going to be setting the marginal posterior distribution for each of the alternatives. So sort of your A posterior, your maximum A posterior estimator is going to be X bar I for that alternative, and then your uncertainty about that alternative has factored in your sample variance, or the variance of each of the alternatives. So 2 cases here, if we knew the unknown sigma I squareds of the normal distributions, then the posterior distributions are each marginally normally distributed. And I'm going to let mu I here denote the posterior mean of alternative I, and rho I squared be the posterior variance here. So you can see that as you take more samples, as Ni increases, the variance of this normal distribution in your posterior is shrinking. And so you're getting less uncertainty about what the true value of the performance of alternative I is. If you, as is more often the case, if the variances are unknown here, you end up with a T distribution for each of the marginal ones, where you have a degrees of freedom nu I, which is reflecting how many samples you've taken at that alternative. So altogether, the posterior distribution we end up with on the unknown problem instance is either a product of normal densities or a product of T densities. And in checking posterior stopping rules, we're going to need to integrate against these product form posterior distributions. So with this posterior distribution on hand, one can then consider different Bayesian selection criteria that assess some way the quality of a given alternative I. 3 popular ones out there are the posterior probability of correct selection, PCS, the posterior probability of good selection, PGS, and the posterior expected opportunity costs, or EOC. The posterior probability of correct selection can be interpreted as the probability that given the data, my unknown problem instance is one for which alternative I is the best. Likewise, the posterior PGS is the probability given the data that my alternative I is has a performance that's within delta of the unknown best, where delta is some tolerance that's specified by the user. Essentially, what's their tolerance towards making a suboptimal decision. And lastly, the expected opportunity cost is defined as the expected difference under the posterior distribution between the performance of that alternative WI and the performance of the best. You can think of it as sort of an expected optimality gap between the performances of alternative I and the unknown best alternative. From looking at these, you can maybe see that we can these would be computed by doing some form of integration against the posterior distribution that we just saw in the previous slide. And these different selection criteria can then appear as statistical guarantees that you want a procedure to deliver. So as a decision maker, I could specify a level 1 minus alpha, so maybe something like 0.95. And the first 2 of these are going to say, simulate until the data tells you that your posterior probability that a given alternative little d, the one I'm going to consider selecting at the end, is at least, I'm at least sort of 95% sure that it's going to be the optimal solution. Or a posterior probability above 0.95 that it's going to be a delta optimal solution. Things flip when you look at the expected opportunity costs. You can imagine specifying an optimality gap beta and simulating until the alternative that I'm going to be choosing has an expected optimality gap less than beta. So these are conditions for terminating a procedure. So here the ranking and selection procedure is being run until the guarantee can be delivered. And I should say that this is in contrast to most of the literature in the Bayesian space, which typically assumes a fixed budget setting. So there, I'm fixing the number of replications or this total sample size, and I'm going to hope to sample in a way that's either maximizing the posterior PCS, posterior PGS, or minimizing the EOC within that budget. Those settings are typically are very useful if you're operating under, say, you have a fixed time to make your decision, or I have X number of dollars to use to rent servers, and there you're working within a hard constraint on your budget. Here, I'm in a relaxed setting where the decision maker is specifying the kind of guarantee that they want to get, and then has the time or the resources to be okay with simulating until we can deliver that guarantee. What's often studied in the fixed budget case are allocation rules. These are ways to tell you where to take samples from next, essentially which solutions or alternatives should you simulate next. And there, the emphasis is often on coming up with allocation rules that are in some way asymptotically optimal. Either they're consistent in that they're going to converge on the conclusion of which alternative is the best, or they're going to be doing sampling rates that are in some, asymptotically optimal. Instead, the focus of this talk is on stopping rules, which I view as sort of an underappreciated or looked over aspect of these algorithms, but I hope to convey that it is actually a decision of some consequence. How precisely do you check the stopping rules? Here's where we sort of see the magic of the Bayesian framework, in that as we want to deliver a Bayesian guarantee, the stopping rule principle tells us that it's perfectly valid for us to take data and stop and select an alternative whenever its posterior quantity of interest crosses some threshold. It's really that simple, that we can monitor or repeatedly compute this quantity and terminate once it crosses some threshold. The advantages of this really can't be understated because we're allowed to just repeatedly compute these quantities without sacrificing any statistical validity. And that tends not to be the case in a frequentist setup when you think of, say, p-hacking, the approach, or the approach of repeatedly computing a p-value and terminating, or taking data and terminating once it crosses some threshold. That's not a statistically valid approach. But here we can get away with doing just that in the Bayesian framework. And second, since the guarantee is being tied up with, or is a result of the stopping rule, it gives us complete flexibility in terms of how we allocate simulations, replications across alternatives. I wanted to give a visual example here. If you think of the case where you have two alternatives with equal variances that are known, then you can write out the posterior PCS or posterior PGS in terms of the normal CDF. And then by inverting that, you can get the following continuation region for these kinds of stopping rules, which is written at the top of the slide here. So on the y-axis of this plot is the difference of the partial sums between replications taken at the two alternatives, and I'll assume that we are taking an equal number. So we take 10 observations of each sample, we check the stopping rule. If it's not satisfied, we take an 11th replication from both of the alternatives and so on. There, the continuation region is telling you when to stop. So you have what is you can view as a Brownian motion that's being observed at discrete points in time, and it's moving around. And once you observe it crossing one of these thresholds, you would terminate the procedure. What's apparent here is that there is a big difference in the shape of these continuation regions for the posterior PCS stopping rule versus the posterior PGS one. The posterior PGS one defines a closed procedure here, because if you're only looking to detect a difference of size delta, eventually you're going to be able to distinguish, you'll have enough precision on the means of the two alternatives to know whether a given alternative is good or not. On the other hand, the posterior PCS one is going until you can conclusively determine that one is better than the other. And so it's going to be this open envelope here with a square root and boundaries.
But if you divide both sides of that inequality by n, now you are expressing everything in terms of the absolute difference between the two sample means.
Yes,
and then the right hand side becomes inversely proportional to root n minus delta in the case of PGS, and there is no delta in the case of PCS.
Right, I should say delta equals 0 for the PCS case.
Yeah, correct. Yes. But anyway, so would that be a better way to redraw the shapes?
You can certainly do that. I chose to set it up this way because the left-hand side term then is then a standard Brownian motion. I guess if I move the sigmas back over, it would be a standard Brownian motion. But I think this is sort of the typically standard framing of continuation regions for these.
Because frequently one thinks in terms of the absolute difference between the two sample means, is that large enough or whatever? So, yeah.
Yeah, there your stopping condition would be, checking when as you said, the difference of the absolute difference, I should say, of the sample means is big enough, then you would conclude one or the other.
Correct. Yeah.
Yes. So despite its popularity in the literature, I wanted to raise some issues with the posterior PCS guarantee. Here, if you had small differences in performances between the best and say the second best alternatives, that's going to lead to longer run times. The way to see that on this previous slide is that the difference in performances is the drift of this Brownian motion process. So if that's small, you have a Brownian motion that is a small drift, and you're simulating until it's crossing one of the blue boundaries. If the drift is small, that can take a very long time. And therefore, it's hard for us to justify that computational effort, the excessive sampling that you're doing, to detect a difference in performance that may be practically insignificant. It's also the case that some practical problems have multiple optimal solutions. This can come up if, for instance, there are different symmetries in the problem and that aren't being recognized. So some ill-posed problems can have this kind of degeneracy of having multiple optimal solutions. And if you were in such a case, running the procedure with a posterior PCS stopping rule would mean you're simulating until a Brownian motion with drift 0 is hitting one of these boundaries. The posterior PGS guarantee, however, has none of these issues. And so for the remainder of these slides, I'll just be concentrating on posterior PGS over posterior PCS. And we'll also still look at posterior EOC. So to get into the checking of stopping rules with these quantities, at face value, you would see that the posterior PGS and posterior EOC appear to be k-dimensional integrals. And therefore, if you were to naively use numerical integration there, that's going to quickly become intractable for large numbers of alternatives. And probably in light of this, a common practice out there is to instead bound the posterior quantity of interest, in particular that of the alternative with the highest posterior mean, which I'll denote by alternative parentheses K, because the alternative with the highest posterior mean is the one that looks the best. That's often the one you're going to end up selecting at the end of the procedure. But in using these bounds, we end up with conservative procedures in that they're taking more samples than would be taken if you had exactly computed the posterior quantity. That then presents a trade-off between simulation time, which is, by that I mean the time that you would spend simulating those additional replications, and time that might otherwise have been spent more precisely computing the posterior quantity of interest. So the motivating question going forward is going to be, where on the spectrum should we fall with deciding how precisely to check the stopping rule? How do you balance this trade-off? To give examples then for this posterior PGS, you would typically be going until posterior PGS gets to be above 1 minus alpha, and then you terminate. So the bounding approach is to come up with a lower bound on posterior PGS and then stop when it crosses that threshold, which will be no sooner than if you had exactly computed the posterior quantity. Two bounds out there are derived from either Bonferroni's inequality or Slepian's inequality. And in each of these, what appears at the end is an expression that has these probabilities of the differences of either a difference of two normal random variables or two t-distributed random variables. In the latter case, when you have unknown variances, it's common to use a Welch approximation to get around this inner probability term. So as you can see, the Bonferroni inequality, you end up with sort of a 1 minus the sum of probabilities. For Slepian's inequality relates probabilities with respect to an independent or a multivariate normal with independent components to a multivariate normal that has positively correlated components, which is what we get here because the differences Wj minus Wk are positively correlated when you look over different values of J. And you end up with then a product of these probabilities. So these are two bounds out there that are used in lieu of exactly computing posterior PGS. But these bounds are by no means tight. And so what I'm showing on this slide here is for different posterior configurations where the true posterior PGS is either 0.99, 0.95, or 0.9, think of it as a horizontal line on this drawing here, these bounds are returning values that in some instances can be well below what the true quantity is. So there are a couple of trends apparent here. For high values of 1 minus alpha, you have a very slight deterioration in these bounds. They tend to be relatively tight. But as you take 1 minus alpha further away from 1, the looseness of the bounds is more exaggerated. Also, as you increase the number of alternatives, the bounds can be weaker in this sort of worst case setting. And of the two, Slepian's inequality tends to be tighter than the Bonferroni inequality. So returning to what at first appears to be a k-dimensional integral for posterior PGS, turns out there are a couple of different papers in the literature that have found that you can actually condition and uncondition on WK, and in doing so, it leads to a one-dimensional integral. But as far as I can tell, this expression hasn't been used in checking stopping rules. So here the posterior PGS can be written by doing the conditioning and unconditioning as a one-dimensional integral where the integrand is a product of k minus 1 CDFs and 1 PDF, where these CDFs and PDFs are either normal distributions or t distributions. And to give a sense of the time it takes to numerically integrate this one-dimensional integral, I have a table at the bottom here showing, that even for numbers of alternatives that are actually quite high for what you see in the Bayesian Rankine selection space, can compute these in fractions of a second. These times here are for the case where you have known variances. When you have unknown variances, the times tend to be maybe 2 to 5 times higher due to the need to compute either a beta function or a gamma function within the t distributions. But the indications are here that it doesn't have to be that expensive to exactly compute this quantity. Then for the posterior expected opportunity costs, there's one bound there in the literature. This is an upper bound here. It goes by the name of a Bonferroni bound, but actually it's not using Bonferroni's inequality to derive it. Instead, it's using the fact that the expected value of the maximum of a bunch of non-negative random variables is less than or equal to the sum of their expected values. So that's the bound in the upper equation there. And from what we could tell, there is not a Slepian's inequality or a Slepian bound on posterior EOC, but we were able to come up with one by using the trick that the expected value of a non-negative random variable can be calculated by integrating over the tail CDF. And so what that gives us is we can replace the expected value here with the integral over the tail CDF. And that tail CDF, the probability that W brackets K minus W parentheses K is greater than delta, that's the posterior probability that alternative parentheses K is delta worse than the best, at least. So it's a delta bad system, which means that's 1 minus the posterior PGS of that alternative. And here I've chosen to use delta as my variable of integration because of its connection to posterior PGS. In this second line here, then there are two ways to proceed. One is to insert our one-dimensional integral for posterior PGS, and that will give us a two-dimensional integral for posterior EOC. I'll show that in just a couple slides. Or we can apply our Slepian's bound here, and that's what we get for posterior EOC Slepian in the last inequality. So there, the Slepian bound is an integral over, again, a product of K minus 1 CDFs. Okay. So in a similar plot here, things are working in the opposite direction, so you want a bound that's smaller. The Slepian bound is, again, tighter here. That two-dimensional integral that you'd get from plugging in the one-dimensional integral for posterior PGS into that previous equation is a bit more expensive to compute, but here it takes on the order of a second or two. And these times should be weighed against the time it takes to simulate a replication in your setting. But this is sort of a new two-dimensional integral to get at this posterior quantity that is otherwise perceived to be very expensive to compute. So I wanted to run through a couple of experiments here then to test the effects of using the exact quantities to check your stopping rules versus checking one of the four bounds here. And although the emphasis of this work is not on allocation rules, we wanted to see if there is any different results you get from using different allocation rules. So we tested 3 here: equal allocation, which is exactly as it sounds. You're taking an equal number of replications from each alternative. Optimal computing budget allocation, OCBA, is an algorithm that samples sort of myopically to either maximize the posterior PGS or minimize the expected opportunity cost of the solution that looks best, under an assumption that if you take an extra sample or an extra observation at a solution, its posterior mean is going to be unchanged, but its posterior variance will have shrunk. And then lastly, Thompson sampling. In this setting, Thompson sampling allocates the next replication proportional to the posterior PCSs of the alternatives. one way to do that is just to generate a random problem instance from the posterior distribution, and you sample the alternative that had the highest mean from among from that problem instance. Okay, so I'm going to be testing a setting with 100 alternatives. The true means are going to be generated from a Weibull distribution. I guess this should be actually WI here. The true means are generated from a negative Weibull distribution. And for these parameters, it's roughly the case that about 1/3 of the alternatives are delta equals 1 good. And then there's this tail of poor alternatives trailing off. So we use splitting to run these experiments, which means that since we know that exactly checking the stopping rule is going to terminate earlier, we simulate the different procedures on the same sample path. So we generate data, we mark when it would have stopped if it was using the exact quantities, and we collect the statistics, but then we continue taking samples until it would stop when having checked the bound. And we also use splitting, so in that extra phase when you're taking the additional samples beyond when you stop with the exact one, we split. So we actually take 50 different further sample paths there. We have a total of 5,000 observations in the plots that follow. And a quantity of interest here that we're going to be plotting is the fraction savings. So I'm defining that here as how many fewer samples would we take by exactly checking the stopping rule, and then dividing that by the number of samples that you would take having used the bounds. So that's S. And to interpret the slides that follow, which are CDFs, if a curve is towards the upper left corner, it's indicating very few savings, while if it's pulled away from the upper left corner, that's indicating more substantial savings. For the posterior PGS, we were somewhat surprised to see that there really aren't many savings to be had by exactly computing that quantity when it comes to using an efficient allocation rule like OCBA or Thompson sampling. So you can see here that for an inefficient procedure like equal allocation, you can get savings on the order of 20, 40% on 10, 20% of the runs here. Again, the way to see this is the further the curve is pulled from the upper left-hand corner is an indication of greater savings. The story is much different for exactly checking the posterior EOC stopping rule. Here we see savings for against the Slepian bound, and even more so for the Bonferroni bound, for all three kinds of allocation rules, where again, equal allocation offers the greatest potential for savings, but there again, it's the least efficient selection procedure, or least efficient allocation rule. And to summarize those values in a table here, the ones I wanted to point out that are for those efficient allocation rules, Thompson sampling and OCBA, exactly computing posterior EOC allows you to stop on average, say about 30, having taken 30% fewer observations when using the Bonferroni bound that's out there in the literature, or an extra 6% savings when using the new Slepian inequality, or Slepian bound that we presented here. So that's it. Right now, it's not something for nothing because we are spending time to exactly compute the posterior EOC, but we're going to figure out how to pick up those extra savings. So our observation is that computing posterior expected opportunity costs, especially after every iteration, that can add up to be an expensive computation. And there's really no use to computing the exact value of this posterior quantity if we don't think it's anywhere close to beta. So if it's really high, far above beta, we know we're probably not going to stop anyway, so why spend the time exactly computing that value? And that led us to the idea of using a Monte Carlo estimator to pre-check the posterior EOC stopping rule. What that means is after taking data, we generate problem instances from our posterior distribution, and we obtain just a crude Monte Carlo estimator of what the expected opportunity cost of alternative parentheses k is. And we check if that Monte Carlo estimate is less than beta, that means if our estimator is pretty precise, that it's a good time to think about stopping. And so we compute the exact quantity then and decide whether to stop or not. But if the Monte Carlo estimator is not less than beta yet, we're not going to bother computing the exact quantity, and we're just going to proceed to take data. This approach of pre-checking with Monte Carlo is not going to invalidate the Bayesian statistical guarantee, because we are only stopping after having exactly computed posterior EOC. What we see then is that in this slide here, I'm plotting the sample size on the x-axis. The Bonferroni and Slepian bounds are these curves out to the right, which show you that those procedures take more samples. And it's hard to see, but the red and the blue curves are actually on top of each other. So the blue curve that's hidden behind the red one is showing the sample sizes from exactly checking posterior EOC every iteration, where the Monte Carlo pre-check one is shown in red. And the positive result here is that the Monte Carlo pre-checking is essentially stopping at the same time as the exact one. But we know that it's not going to be computing the double integral every time. And in fact, if we look at it from the perspective of what's the time spent checking the stopping rule, we see that the exact method here, that adds up to quite a lot of time spent calculating the double integrals. But Monte Carlo pre-check, the red curve there, is able to spend far less time checking the stopping rule, because it only needs to compute the double integral probably a handful of times. And so we're seeing here for this k equals 100 example of something like 100, I guess about 3 to 5 minutes spent checking the stopping rule, which you think is a worthwhile investment considering you're saving something on the order of either a couple hundred or 1,000 simulation replications. So these should be compared against what the time it takes to compute a simulation replication is. Pushing that idea a little further, one might wonder, well, why compute the exact quantity at all if we think the Monte Carlo estimator is pretty good? Why not just use it to directly check the stopping rule, by which I mean terminate whenever your Monte Carlo estimator crosses some threshold? The appeals or the pros of this is that we would expect to get a sample size that's comparable to exactly checking the stopping rule, but we essentially have none of the cost of doing that. So we get computational times that should be comparable to using just Bonferroni or Slepian bounds, because the calculating of the Monte Carlo estimator from sampling is a trivial operation. The cons of this, though, are that it's going to invalidate your Bayesian guarantee. The reason being that this Monte Carlo estimator is a random quantity, so it's subject to random error. And that means you may not actually be stopping at a time for which your posterior distribution says you've collected enough evidence to meet your guarantee. But we do recommend this as a practical approach with sort of a two-part justification. The first is that when you use bounds like Slepian and Bonferroni, they still have the difference of two t-distributed random variables. And so they use a Welch approximation to compute those bounds. Simply by using that approximation, you've sort of undermined your Bayesian guarantee, and then it's not entirely rigorous anymore that the bound is going to truly be an upper or lower bound of the posterior quantity that you're looking at. But perhaps a more practical side of this is thinking about what happens when these assumptions that we started with do not hold, for instance. So if you get rid of normally distributed outputs assumption, you can no longer use Slepian's inequality because that relies on a normality assumption. And if you aren't doing independent sampling, if you're using common random numbers, or as we discussed earlier, if you didn't have independent beliefs, you lose the product form in that posterior distribution, which means you can't do the conditioning trick to get either a 1 or 2-dimensional integral for these posterior quantities. So that means you can't exactly compute the posterior quantities, and really the only game left in town is the Bonferroni bounds for these quantities, which we've seen to be among the most conservative. So if the options you have available to you are use a Bonferroni bound on posterior EOC and take an extra twice as many samples versus using Monte Carlo estimator and stopping pretty much when you would if you had exactly computed it, we would advocate for using the Monte Carlo estimator directly there. And in support of this, we implemented that procedure of using the Monte Carlo estimator to check the stopping rule, and we see that the posterior EOC upon stopping, when you're looking for a nominal target of less than 0.5, there's really only a slight deterioration in that Bayesian guarantee from using only the Monte Carlo estimator. So the main takeaways or contributions from these ideas here are that we came up with a cheaply computable Slepian bound on posterior EOC, as well as a double integral for posterior EOC. We observed that savings relative to using bounds on posterior PGS tended to be minimal, which was a surprise to us, but the savings from using the exact quantity versus bounds on posterior EOC can be quite substantial here. And you're actually able to pick up those savings at a little extra computational effort by using a Monte Carlo estimator to pre-check the stopping rule. And lastly, as I just said, if you're in a case where some of these assumptions don't hold, then a Monte Carlo estimator can be an attractive option. Thank you. I'll take questions now.
So I have a question. So Slepian's bound basically replaces all non-negative correlations with zeros. Now you can sharpen the Slepian's inequality instead of replacing them by zero, by replacing by the minimum correlation.
Okay.
So I don't know if that would improve the accuracy anymore or what, but it may be something worth looking at.
Okay, I wasn't aware of that.
Yeah, just replace the so you can show that the one-sided, it's called, the Slepian's paper is called one-sided barrier of noise or something like that.
Mm-hmm.
And the one-sided probability can be shown to be increasing function of every correlation. So you can just replace the correlation by the minimum correlation. Yeah. Now you can't do that for two-sided case. Then you got Sidak inequality. So in that case, you can't just replace by minimum rho. You have to replace with rho equal to 0. But you may want to look at that. The other thing I wanted to say was this, that Slepian's inequality basically treats the random variables as independent when they are actually positively correlated. Now, there are a whole slew of papers which kind of generalize this idea to introduce positive dependence, where you don't need normality. And that if the variables are positively dependent, there's a definition that was originally given by Eric Lehman back in 1966, where you replace, you can replace the probabilities by the joint probability by a product of the probabilities. So in that case, you don't need normality.
Okay.
So, yeah, you can extend the results that way.
Is that related then to sort of positively associated random variables as well, a different, where you have positive correlation, but it doesn't assume normality?
Correct. So you don't, you don't even need positive correlation necessarily. There is a definition of positive dependence, which is pretty general actually. So you may want to take a look at it. I'll be happy to talk to you in more detail later.
I'd like that. Thanks.
David, in listening to your talk, I kept trying to think about why expected opportunity cost is so much harder than, what we've been doing based on Peter Salemi's work and Enhei Song, where we stop when the expected improvement is less than or equal to a threshold, right? And that's a marginal quantity, and it's actually what we compute for sampling anyway, so there's no additional effort for that kind of a stopping rule. Why is EOC is a joint statement, right? Is that the issue?
Yes, I think from looking at it before, it had to do with the identity here. So the brackets K, the best alternative, is not one that's known to us. So we're having to take an expected value over the posterior distribution, not having known that quantity. I want to say that expected improvement, I'd have to look at the equation, but I thought that one is relative to sort of the, you've plugged in the solution that looks the best and its posterior variance. Is it then a marginal statement because you fix this index?
That's right. The key thing is that you say, if I stop and I choose this one, it doesn't actually have to be the one that looks the best, but we typically do that. If I stop with this one, what's the expected improvement versus each alternative? And that's just a marginal calculation. There's no numerical integration or Monte Carlo needed. But yeah, so it's because of this joint statement. Okay, thanks.
I was thinking the same thing when I had seen Mark's talk. I think there it informs.
Yeah, I just want to add one more little thing. So I mentioned that Slepian's inequality can be sharpened by replacing the all the rho ij by zeros by the minimum rho ij. Now, but that makes the correlation equal. So if the correlation is equal, then you get an iterated single univariate integral. You can express the one-sided probabilities of equally correlated variables by a single integral. So instead of product, you got one extra integration involved. So it adds a bit of computational complexity in there. You don't, instead of just taking product, you take an integral of the product. You have to,
Yes.
you have to introduce you have to condition on a variable that causes the common correlation. And then you have to condition on that and then uncondition on it. So that makes it a single integral. But it's not big extra computational cost, but might be. So that's why I said worth looking at.
So if I'm following, that might be similar to what's done here, where you're conditioning on one of the performances, and then you end up with an integral of a product.
Correct.
There.
Yeah, it looks very similar. Yeah.
Okay. But here I'm guessing there would be these CDFs would probably all look the same because you are giving them the same correlation sort of.
Yeah. Yeah. Correct. Right. Okay. Right. So it could be just f to the power of something rather than product.
Okay. Yep.
By the way, I should mention that I come from Cornell,
Right.
where I was a student of Bob Beckhofer, who's kind of the father figure of the ranking and selection.
Yes.
So I was one of the early students of the Bob Beckhofer, and so anyway, I shouldn't say I was an early student, but I was a student. Yeah, that's how I'm familiar with all these calculations.
Yeah, I figured you would be one in the audience to certainly be, have seen many of these ideas before.
Yeah.
So, dude, I have like a 4 steps away question, but let's say that someone was, instead of deciding where to stop, but was sending a bunch of things to a cluster and deciding how many to send. Could a lot of these be inverted that way to make that decision easy, or is it pretty hard to invert them that way?
So one idea I have, and maybe it's not directly answering your question, is that these exact quantities could be used in the allocation rules. So allocation rules like OCBA would tell you how many replications to take of each solution. And there, what they use is a Bonferroni inequality, or I guess in the PCS case, the Slepian inequality. But they're using bounds, and then they work from that to come up with what the proportions are for the sample sizes of the different alternatives. I think if you were to plug in, these integrals, you might be able to get an allocation that comes out of that.
Okay.
Which would tell you how much to sample each one.
Yeah. There's probably a few question marks along the way, but that's what I was going for. Thanks. All right. We are at 12:20, which I think is our ending time. So I'm going to close this out here. David will be around in whatever sense around means anymore. So feel free to shoot an email, do a Zoom chat if you have any follow-up questions. With that, we'll do our individual applause and thank David. All right. Thank you, everyone.
Thanks.
Bye.
So, question for you. Oh, hey, Kang-Han. You're home today. Me too. All right, see you later.
I just realized I was muted.